Good afternoon, everybody, and welcome to this re-recorded version of the virtuals lecture that we had on June 23rd, 2021. So if you haven't seen yet, I did stream that day. We did have class, and if you weren't there, unlucky for you because the stream did not get saved. That was a mistake on my part, but it couldn't be avoided. And so now I'm going to re-record this session for anybody who comes back to rewatch later. All right. So the class we had on the 23rd was an hour and 30 minutes long. This one will probably be shorter than that, maybe even much shorter. The reason being I'm not going to be able to answer questions. So I'm not interacting with the chat. We're going to kind of speed through some things here. We also have a Golden Knights game here coming up, so I'm gonna make sure that we stay on topic and we kind of speed through this. So the first thing that we talked about yesterday was this CS202 string homework that you guys have been working on. Now this one is due as officially yesterday. It's been changed to Saturday and Sunday night, so you may still be working on this assignment. And if you check the Discord, you'll notice that I sent this function that we're looking at right now, the concatenate function. I pretty much sent that to you in the Discord. So if you weren't in class, I think it's only fair that I describe to you what I did. And yes, you can use that concatenate function that I sent in the Discord if you'd like. Completely up to you. Hopefully, as I discuss how to do this function to you, it might help you kind of figure out the other functions, all right? So this is what we're going to start with today. So this concatenate function, as you can see, I've got some work all the way going up here. Got some work already going on. So I'm going to uncomment these real quick. So pretend somewhere in our code we're going to have this CS202 string P. We're going to have Patty. That's going to be the string that we're working with. And somewhere we're also going to have this CS202 string W, which is going to have Willa in it. All right, so we've got Patty and Willa. So if we call concatenate, which is called like this, recall that the CS202 string, if I pull up the header file here, recall that this is a static function, all right? So if it's a static function, I'm going to go ahead and call it by using the scope resolution operator. And I'm going to concatenate this string P with this string W. Now, what does that produce? Well, it produces this string. It produces this string. So new S, in fact, is going to be a string that's looks like 5 plus 5, so 10 characters long, in which the string on the left side is up front, and the string on the right side is in the back. All right, so that's what this concatenate function does. You've probably used just regular strings before, right? So if this wasn't a CS202 string, but it was rather just a string, concatenate in general is called like this. You would say string is equal to P plus W, right? So that's what we're doing. That's exactly what we're making. So the first thing that we need to do is make a new array, right? So the left array, notice that these are both constant. We're not going to be editing these. We're also not going to be making shallow copies of them. We have to allocate brand new memory for these arrays. So if you go look in L.carArray, in here you probably have Patty. This is, of course, just the example. And if you go look in R.carArray, you're going to have Willa, all right? We also have access to the L.size, which is probably, in our example, 5. And we also have access to our R.size, which is, guess what? Probably 5. At least for this example. And we're going to make a brand new CS202 string, all right? So let's actually go ahead and declare that right now. I kind of did it a little backwards yesterday, but I like to mix it up a little bit. And let's say this is going to be our return string, all right? Now recall that this is going to be created with the default constructor, all right? And I think I require you to fill in the default constructor up here. But recall that this is not going to do anything really. It's just going to initialize the size to be 0. And it's going to make sure that that car array, that pointer that we have, right? This pointer, it's going to make sure that it's pointing at null pointer. All right? It's going to be making sure that it's pointing at null pointer. So officially down here, we have just a default return string. It has nothing in it. And so now let's go ahead and allocate the memory for our return string, all right? So I have access to its private variables because this is a member function. And so there you have the car array, right? And so if we want to allocate memory into there, we're going to do that. Now, how big is it? Well, it's probably going to be 5 plus 5 equals to 10, right? But since we're making this function work for a bunch of different cases, let's make that equal to the left size plus the right size. All right, so that allocates, that's going to allocate, in our example, a nice open array of 10 spots for 5, 10 spots. That's a nice empty open array, 10 spots. So now we're going to copy this string into the first 5 spots, right? Now I apologize. I believe my computer is still recording. So just give me a moment to confirm that we're still here. It looks like we are. I'm going to write down this timestamp because I just want to make sure. All right. I think my computer, my OBS had a little bit of a freeze there. So I'm just going to make sure it works. So, as I said, we're going to take this patty, right? That's also an array. And we're going to copy those first few characters in there. So, we're going to need a for loop, right? Now, recall that Willa's going to go up in these spots, so we're actually not going to go through the whole array yet, all right? So, we're going to do a for loop to start. Equal to 0, I is less than, well, we're only going to go up to the first 5 spots. How big is that? Well, that's the left dot size, right? That's the left dot size. And now we're going to copy in those characters. So let's go ahead and refer to our return string here, located at I. And let's say let's go ahead and that's equal to our left car array at index I. All right. So after that for loop, we're going to have this, right? After that for loop executes, we're going to have Patty. Patty's going to be copied in there, right? So on the first for loop, this will be P, and then A, and then T, and then T, and then Y, and then done, right? The for loop's over, and we still have 5 empty spots to go. So now it's our job to copy in Willa. Now this one is a little different, right? Because notice that they no longer line up. They no longer line up. So that first one was super easy. But now it's no longer easy because this is at index 5, index 6, index 7, number 8, and number 9, right? And if we look at the Willa string, this stuff is at index 0, 1, 2, 3, 4. So if I said something like this, if I said return string, I'll just copy this down here. If I said, you know, this at 5, let's say I is equal to each other. So if I said 5 is equal to 5 on the right character array, it's not going to work, right? Because this is the right spot, but there's no 5. I mean, there's no index 5 in this string, so that's not going to work. So what if I started at 0, I equals 0? Well, then I'm going to overwrite this, right? Right, so if I said return string at 0 is equal to this string at 0, I'm then going to overwrite my P, and I'll put a W there instead. So what we need is some for loop, which is going to allow us to assign the 0th index at 5, the first index at 6, the 7th index here is going to be equal to number 2. So we're going to go ahead and do that part now. So I'm going to say for int I is equal to, and I would like to start at this location. I'd like to start at this location. But we don't have to. I actually did that in the other example. So check the Discord if you want to see what I did yesterday. I'm going to mix it up for now. Let's try a different method. So instead of starting at 5, let's start at 0. And instead of going up until 10, let's just say while we're less than the right size, right? While we're less than the length of Willa, and we'll say I++. And so if I put an I in here and I put an I in here, things will go well for this side, right? But if I don't edit this, we're going to end up with a W. We're going to end up overwriting our stuff there. So I need to add something to it. Do you know what I add? Well, the L.size. So what is this going to do for us? Well, that's how many, that's how big the first string is. So if we start at I is equal to 0, and I add L.size, which is 5, 0 plus 5 puts us right here. So then we're going to say W goes here. And then what's next? I is equal to 1. I plus 5 is 6. So at the 6th location, it's equal to 1. 6 equals 1. So we get the I. We're going to say 7 is equal to 2. That's the L. 8 is equal to 3. That's the L. And 9 is equal to 4. That's the A. Just like that, folks. So now we're almost done. The next thing we need to do is adjust the size in the return string to make sure. So we're going to take the return string. We're going to access the size, and we're going to say, hey, we know what the new size is. It's equal to the left size plus the right size. And then we can return the return string. And that's it. All right. Just gonna save it, and I'm gonna zoom out just a little bit so I can see it. And if I end up deleting all these comments, which you probably won't be happy about, but I like to make my code look a little more condensed. The first thing we did was we created a return string. We allocated some new size for that array. We then copied in Patty. Then we copied in Willa. And then we adjusted our size, and then we returned it. All right, so that's the concatenate function. So after hearing me walk through this one with you, hopefully you can get through the rest of these functions. I know many of you have already. So that's that. Now, what I have to do basically is cover exactly what I covered yesterday. In the same order, and I have to do kind of the same notes, all right? So I'm going to kind of be going off of what I did yesterday. But I'm going to pull up the notes that we had from the 22nd, all right, when we did talk about virtuals. We discussed a polymorphism, right, as something that has many forms. And we began talking about virtuals and abstract classes, right? I don't think we got to an example of that, so I'm going to do that today. Actually, we did get to an example of that on the 22nd, but we're going to have more examples today. So recall, when we're talking about virtuals, we always have class and inheritance involved. If we don't have a class, no virtuals. If we don't have inheritance, no virtuals. There's always dynamic memory involved. That's how we invoke virtuals, all right? That's how we make virtuals work. There's always a pointer to the base class. Why do we need virtuals? Well, is there some way that an object can take the form it needs during runtime? Yes. If you recall back to the inheritance code with the players, right? We had the warrior, the ranger, and the mage. Those three classes that all inherit from the player. We kind of want to have just one object. We say this is a player, and during the runtime, if that player can take the form of whatever it is, say the ranger, so that it can invoke its special ability, that makes our life easy. That makes our life easy. So today, you know, as on the 22nd, we discussed that we're going to fix the gamer code today. That's exactly what we're going to do. As you can see there, I put that note there. So, we're just going to kind of run through all of the notes real quick so we can get that out of the way, and then we'll do an example of everything. There's one thing it looks like I added, so let me put that in here. Only functions and destructors can be virtual. No constructors, no variables, nothing like that. Alright, so I'm going to start adding some formatting in here. And we're going to refresh our minds on the virtual function, which is what we talked about yesterday. So this is a function in the base class that is listed as virtual. As you kind of remember, this is the example, maybe some sort of example we went over. I think we went over the shapes, right? We went over shapes. Let me even pull that up here to see how far we got. I did download the notes from that day, so we are right on schedule. We should be. If I go to my lessons here and I pull this open, I should see this. Yep. So if you recall, up here we were messing with the virtual destructor. We haven't talked about that yet. We haven't talked about that yet. We will get to that. But we did talk about this one, right? That's what we talked about on the 22nd. So we were making this print shape thing virtual. And we had declared a square class. And we made it do a print shape. And we also declared a square2 class, and we made it print a bigger square. And then we messed around in here with some of that stuff. And if you remember, we've decided that as long as the base class contains some virtual, it's always going to follow the chain of inheritance. So please review that in the YouTube video if you need. So that was the virtual function, right? So that's what's in our notes here. Recall that the virtual functions will always be overridden in the derived class. That's, in general, why something would be virtual. If we had a virtual in our base class that never got overridden, it really wouldn't make much sense. Why is that there, you know? And then also here, I gotta fix this. I don't know why it looks like that. The overridden in the derived class does not have to be virtual, right? So if we recall that, here's our overridden function in the square class, right? Print shape. Notice that in this class definition, it's not virtual. It's not virtual. It's also not virtual here. As long as it's virtual in the base class, we're okay. And then here's our plain English explanation, right? If the function is specified to be virtual, the program will follow the inheritance chain down to the type that's stored within that pointer. If we stored a square 1 in that pointer, it'll go down to the square 1. If we stored a square 2 in that pointer, it'll go down to the square 2. So now we're going to talk about the thing that you kind of saw there, the virtual destructor. Something you kind of saw there. So what do we know about virtual destructors? Well, this is the same thing as a virtual function. It's the same thing as a virtual function. And you say, hey, well, if a destructor can be virtual, can the constructor be virtual? Well, a constructor does not need to be virtual. And the reason for that is, if you remember from inheritance, whenever we create an object of the base class, or the derived class, if we create an object of the derived class, the base class constructor is always called. It's always called first, even. So we actually don't have to enforce any kind of calling that's going on here, right? Kind of in this program here, the whole point of allocating a new square into the pointer and then calling print shape. The reason that we do that, the reason that we call print shape is because we want to make sure that even though this is just a shape pointer, I want to make sure that I'm calling the print shape from the square2 function. I want to make sure I'm calling this function and not this one up here. But the thing with the constructor is whenever I call this the square2 constructor, right? It's going to call the shape constructor very first thing. And then it calls the square constructor. And then it calls the square2 constructor. So we actually have no need for virtualization with the constructor. Excuse me. We have no need for it. And that's because these always get called first. But why the destructor? Why the destructor? Well, if you recall, destructors go in reverse order. So if this is the construction, it's a little small. If this is the construction order of our square2, what is the destruction order? Well, the destruction goes like this, right? It goes square2. It's like a pyramid, right? And then it goes to square, and then it goes to shape. So notice the very first thing that's alive is the shape, and the very last thing to die is the shape. It's like a little pyramid. It goes all the way up the pyramid, and then it goes all the way down the pyramid. Now, if this was not a pointer, recall, as I said on the 22nd, which was Tuesday, as I said on Tuesday, if we didn't make this a pointer, for example, if we stored a mage in the player class, right? If we said shape is equal to square, and then later we call sPointer.printShape, since we're not using dynamic memory, right? We're not using dynamic memory. This is a static variable, all right? This right here is a static variable. Because we're not using dynamic memory, this is going to call the print shape from the class that we don't want. It's going to call this one. So similarly, if this object goes out of scope, once it gets down to the end of this program and it goes out of scope, can we guarantee that it will call the shape constructor or the square constructor? Can we guarantee that it's going to call the square destructor? I think I mixed up my words a little bit there. Let me repeat that. Since we called the square constructor here, we guarantee that the shape constructor was called and then the square constructor was called. So we already know that. But when this object goes out of scope, can we guarantee that the square destructor gets called? Well, the way we have this now, it's going to completely skip the square destructor. It's going to go straight to the shape constructor. And so, in that sense, we have need for virtualization. We have need for virtualization on that destructor. We have a need for it. We have a need for it. And I'll show you exactly why. I'm going to give you a nice example of that after we finish our notes. So we need this to enforce the order of destructors. You guys want to say hi to Patty? Let's see. You see her? There's Patty. She's a celebrity in this class. We were just talking about her during the strings homework. Now, what else? When is enforcing the order of destructors most important? When is forcing the order of destructors most important? Well, this is a test question, and the answer to it is this. I'll put it in more tab. When the derived class contains dynamic memory. when the derived class contains dynamic memory. And I'll show you why. So here's our syntax for that. And today we're going to kind of develop just a new little code here. A new little code. All right, so I do want to type these out as they are, just so you can fully understand what I'm saying. So to start, I say pretend we have a class A, and let's say this A has a constructor. It doesn't even need a constructor, all right? But let's say it has a constructor. It doesn't do anything. And let's also say that it has a destructor, A. And in this destructor, we'll say goodbye to it. We'll say goodbye, A. Have a nice life. All right. So we've got our constructor and our destructor in here. Maybe we'll even say hello, A. Hello and goodbye. Just so I can really establish the idea of the constructors as well. All right, so there's our object, there's our class. Not an object, but a class. This is our class. And now class B is going to inherit. Class B is going to inherit from A. And so what did I say in the notes? When is that destructor order necessary? Well, I said if the derived class contains dynamic memory. So here's my dynamic memory, right? This is a dynamic array, right? And so I'm going to allocate some memory in there. So this is our constructor, and in our constructor I'm going to say first off, hello to B. It's good to see you. And then I'm also going to allocate just some memory into there. You know, it could happen. You never know. Let's say we're going to allocate 10 integers into that array. Now I have to call new, otherwise it won't work. And now, since we've allocated memory into this class, the destructor should probably clean that up for us, so we don't have to worry about it. So we're going to go ahead and kind of do the same thing up here. So I'm going to say goodbye to B. And then I'm actually going to delete this pointer array. I'm going to delete it. All right. So there you go. There you have it. And so now we're going to do our virtual stuff. So notice there's no virtuals in here yet. There's no virtuals. So let's pretend like we're going to do virtuals anyway. All right. Let's pretend like we're going to do virtuals anyway. So I'm going to have a pointer to A. This is going to be my pointer. And I want it to be equal to a new B. All right. And then down here, I'm going to delete my pointer because I don't want any memory leaks. So notice here we've got a pointer to the base class, right? That's how virtuals work. If you want to come check this, where does it say? Virtual functions need to, dynamic memory is always involved. There's always a pointer to the base class, all right? So there you go. We've got our pointer to our base class. And we're going to allocate a member of the derived class into that pointer. So I'm just going to run this program. Where does the destructor get called? The destructor called here. And where does the constructor get called? Well, the constructor gets called here. So in a perfect world, we should say hello A, hello B. And then we should say goodbye B, goodbye A. You remember that? I was talking about it here. It goes up the pyramid and it goes down the pyramid. So we're going to say hello A, hello B, goodbye A. So let's run it on Bobby and let's see how well we did. All right, we're doing a re-record here, right? Should have just saved it, didn't I? Which one am I saving? Probably saving the wrong one. Whoops. There it is. All right. So I'm pull that onto Bobby here. And we're going to do our favorite compile statements as always. vd.cpp. It's going to do this and we're going to run it. So notice here, our pyramid didn't work. Our pyramid, it did not work. Didn't work. Why didn't it work? Well, because that destructor is not virtualized. It's not virtualized. Remember, we decided that even though we're using dynamic memory, if there's nothing in A that's virtual, it's going to assume that this is A. It's always going to assume that. So in comes the virtual destructor. Okay? Now, I'm going to show you on Valgrind why this is a huge problem. Notice we lost 40 bytes. Definitely lost 40 bytes. Why did we lose 40 bytes? Well, in that constructor for B, which definitely gets called, right? Hello B. In that constructor for B, we definitely allocate 10 times 4, 40 bytes. But we never see this destructor get called. So we never call delete, and therefore we have memory leaks. And that is the sole problem, all right? On a test, when I ask you that, I'm going to ask you on a test. I'm going to say, when is forcing the order of destructors most important? When the derived class contains dynamic memory. So how do we force the order? Well, let's just make it virtual. We're going to make it virtual. And guess what? It's going to work now. It's going to work now. I assure you. So we're going to compile our code again. We're going to run that code. And notice we saw it. There's our pyramid, right? Hello A, hello B, goodbye B, goodbye A. There's our pyramid. And if we run that with Valgrind again, you will see that all heap blocks were freed. All right? So that is the virtual destructor in action. So now we're going to talk about a few things. We're going to talk about the pure virtual function next. Now, a pure virtual function is a little bit different than a regular virtual function. So recall this, that all regular virtual functions have bodies. Did you know that? Well, let's go check our basic code. Remember this? Remember that this function here is a virtual. Notice it still has a body. Sorry, it's not there. Where is it? Here it is. It still has a body. It still has code. It still has that code. So what makes a virtual function different from a pure virtual function? Well, pure virtual functions do not have bodies. They do not have bodies. But other than that, it's the same thing. Other than that, pure virtual functions do the same thing as virtual functions. Do the same thing as virtual functions. All right? So what is the syntax for that? Well, pretty easy. It's that. Virtual type, and then instead of giving a body, you're going to say that's equal to 0. All right? We'll do an example of that. But before we do that, we have to talk about a few more things. Next, we have to define what an abstract class is, all right? What is an abstract class? Well, an abstract class is any class that contains either a pure virtual function or a pure virtual destructor. Now, we haven't talked about the pure virtual destructor yet, but I will get to that in just a moment. I have to define an abstract class, all right? Abstract class is any class that contains either a pure virtual function or a pure virtual destructor. What's so special about abstract classes? They cannot be instantiated. Meaning, we cannot have an object of an abstract class. All right? That's what that means. We cannot have an object of an abstract class. So if I went in here, now let's just do the abstract class thing real quick before we talk about the destructor. So let's say I made this. I wanted to make this pure virtual. All right, well, all I'm going to do is this. I'm going to add that equals 0. And now immediately we have a problem here because we are not allowed to have a body for it. All right. We're not allowed to have a body for that function. So now this is a pure virtual. Yeah, you see I've got the note there already. I should have deleted it. I'm sorry. Now we have a pure virtual. It's equal to 0. And now guess what? If I come down here and I say shape is equal to shape, guess what? We're going to get a red line. And what's that error say? It says object of abstract class type shape is not allowed. And it says that the print shape function is a pure virtual. Indeed. Indeed. So, that is what an abstract class is. Now, why do we need abstract classes? What's the point of having this? Well, here's my best example for you. I don't really think there's something out there that is a shape. Let's use a different example. You know the term entity? Entity can represent anything pretty much. Anything is some sort of entity. My phone here is an entity. My ruler here is an entity. Everything is kind of already an entity. But there's nothing that is just an entity. There's nothing floating around in our universe that's just an entity. So in the same sense, there's nothing floating around in our universe that's just a shape. It's classified as something. It's a square. It's a polygon, a circle, a triangle, a trapezoid, something like this, you know? And you know, when we try to call print shape on something that's just a shape, what do you want me to do? You know what I mean? I said the universe implodes there, right? You can see my implodes. The universe implodes. Because there's nothing out there that's just a shape. There's nothing out there that's just a shape. So it kind of makes sense that we can't have something that's just a shape. It doesn't really make sense. It says, I would like a shape. And they say, well, what kind of shape do you want? There's nothing out there that's just a mammal. Can I have a mammal, please? Well, what mammal do you want? Whale, cat, dog, ox, horse. You know what I mean? So that's kind of my explanation on why we have things like abstract classes. Now, even though a shape is an abstract class, we can still have a pointer to it. We just can't allocate something where we can't allocate an object of that class into the pointer. It must be of the derived class, Okay, so now that we've gone on through that, let's look at destructors, So finally, we're going to talk about the pure virtual destructor. So, here's what I'll say. Works the same as a virtual destructor and a pure virtual function, meaning this allows virtualization of the destructor, right, to enforce the order. Works like a pure virtual function too. In the sense that makes a class abstract. All right, makes a class abstract. Except there's one thing that's odd about this. Unlike the pure virtual function, the pure virtual destructor must have a body. And you say that's annoying. So how is this then different? How is this then different than just a virtual destructor? Well, like I said, it makes the class abstract. But why does it have to have a body? If the pure virtual function doesn't have to have a body, why does the destructor have to have a body? Well, do you recall, come up here, if I have a pure virtual function like print shape, we may never call print shape on just a shape. In fact, we can't. We can't at all. There's no code for it. We can't call it at all in any way. But do you remember that a destructor is always called? You see that? No matter what, this destructor here is always going to be called. It's always called. So we can't just say there's no destructor. We can't do that. It's not allowed. Our code must enforce that there is a destructor for this class, even though it's abstract. So in a weird way, here's what I'll say. In a weird way, we can make, so let's say it this way. Assuming our class has no functions, right? I kind of gave you an example of that, right? Where's my class that has no functions? Here's my class that has no functions, right? It has a constructor and a destructor. This has a constructor and a destructor. So in a class that has no functions, having a virtual destructor allows us to make it abstract. Even though the destructor will have a body. The destructor will have a body. So the syntax for that is this. And the body must go outside of the class. All right? The body must go outside of the class. So we're gonna do that. Let's just use our other example instead of whatever I was doing here. Let's do this one. I'm gonna make this a pure virtual destructor, and then I'm gonna move the body outside of the class. Hey. All right. So this is a pure virtual destructor up here. And I'll run this code so you can see what it does. Notice our pure virtual still has a body. But guess what? If I come down here and I say new A, please give me an A. It says, hey, this is an abstract class. This is an abstract class. Can't do that. But if I declare that B, and then I pull it into Bobby and I run it, we're still going to see that destructor being called. Why is that? Because the destructor of the base class is always called, right? We know this. We know this by heart. So notice there, it got called. We saw it got called. Even though it's pure virtual, it got called. So that wraps up our discussion for that, all right? Now, of course, I didn't answer any questions, so we're kind of ahead of schedule. As I said, this video is going to be a little shorter than normal. So if you need to reach out to me, please do so we can talk about it. But what we're going to do now is we're going to fix the gamer code. I said I would do that on Tuesday, and so I'm going to do it now. So let's fix the gamer code. So recall, we kind of talked about this yesterday. I told you the exact reason why. Maybe I didn't. So maybe I'll do a quick review. I thought I talked about it. Maybe I didn't. So if you remember this gamer code that we did a while ago, if I run it, the mage, the warrior, and the ranger, they all had special abilities. I think I did talk about this yesterday. They all have special abilities, right? And our problem is the mage is using their special ability no problem, but the ranger is not using their special ability at all. And we determined why that was. Why is that happening? Well, when we call deal damage from the mage, we go up in here and notice that this is a player object. This is not a ranger object. This is a player object. So we call receive damage from the player class, not from the ranger class. And so even though we know that's a ranger, it's not going to invoke its special ability. So one easy fix for that was we could do a function overload for it. So now the mage class has two deal damage functions. It has a player and it has one for a ranger. So now if I save this and I run this code, we're going to start seeing that special power from the ranger. There it is. You see? Our ranger is now dodging, right? Our ranger is now dodging. It's dodging. So obviously we're calling this overloaded version here. And I said, imagine we're playing a game like Overwatch where there's like 30 characters. Do I really want to overload this function 30 times? I'm just going to copy paste it. What goes in here? Well, Roadhog goes in there, right? Do I really want to copy paste it again? What goes in here? Well, Tracer goes in here. Next thing you know, our code is 17,000 lines long because we copied all these overloads in here. So what do? We say, hey, you know what? Scrap this. I don't want it. I only want one function definition for deal damage, and I'm going to use virtuals. So let's fix the gamer code, all right? We're going to fix the gamer code. Here's our starting spot. Our starting spot is here. Our mage is using a special ability. The mage is using the special ability, but the ranger is not using their special ability. So we're going to fix the gamer code. So what's the first thing that we know about virtuals? Well, the first thing we know is that there's always a base class, right? There's always a pointer to the base class. So we're going to have a player pointer here. Player R is equal to new ranger. All right, so that is our fix number one. So we're going to make all of these players pointers. We're going to make them all represented by pointers. All right, so now that we have pointers to the base class, pointer to the base class, pointer to the base class, we're going to allocate members of the derived class, ranger, warrior, mage, all into the pointers. Next thing I'm going to do is I'm going to delete them at the end because I don't want any memory leaks. So say goodbye to M, say goodbye to R, and say goodbye to W. All right. Now, what else do we have to fix? Well, these are pointers now. They're not objects. They're pointers. So we're probably going to do this instead. Now, this is mad because I'm passing in a pointer instead of an object. Well, we actually have to fix that. I want this to be pointer. Why does this have to be a pointer? Well, we want to virtualize it. So instead of using an object, I'm going to use a pointer. I'm going to do the same thing, not up here, but in the base class here. All right. And then finally, what's the very last thing I have to do? I have to make things virtual. Well, I asked yesterday, what things would be virtual? Well, we go ask ourselves, in the derived classes, which functions are overridden? Looks like receive damage is overridden, and it looks like deal damage is overridden. So let's make those virtuals. Now, since these already have bodies, notice they have code. I'm not going to make them pure virtuals. I'm actually just going to make them virtuals. I think in this example, it's easy to assume that there could be just a player, a player with no special abilities. I'm just a 7 health guy who doesn't have any special abilities. Alright, so I'm not going to make this an abstract class. So now that they're virtual, we're good to go. We've officially fixed the gamer code. So we'll come in here. We're going to compile that. We're going to run it. And we're going to see that right off the bat, we're doing some dodging. And right off the bat, we're using some critical strikes. And notice that it's all working as expected. So all we had to do was change everything to use pointers. Change everything to use pointers. And then we had to go up top here and we have to say, hey, these guys are virtual functions. All right? That's all we had to do. And that wraps up everything that we talked about on the 23rd. That wraps up everything we talked about. Now I'm ending about 40 minutes early, and that's because I really sped through this. So I'm just going to kind of take a second to review the Web Campus files to make sure that I didn't miss anything that I thought we should have talked about. We talked about the shapes, we talked about the virtual destructor, we talked about the gamer, and we got through all of our notes. On top of that, I even went over that strings thing with you. I even went over that strings assignment with you. So that's all. That's all I'm going to record for today. So thanks for watching this video. You know, if you didn't come to class, thanks for catching up. I hope this was helpful. I'm always available to chat if you need some help. And I hope you guys have a great day. Go Knights!